Welcome to the course Business Analytics and Data Mining Modeling using R. So, in the previous lecture we were discussing classification trees. In particular, we were doing an exercise in R for the same. So, we did some modeling using the promotional offers data set. So, we talked about the way we did modeling there, especially the pruning part. So, we were specifically focusing on the pruning part, and there when we try to prune back the full grown tree to a level where it does not overfit the data or fit the noise, the way we followed the pruning process, that was a sequence of pruning was as per the node number ordering, and it was not the nested sequence, right. So, we talked about a bit about this in previous lecture, where we discussed that if this is our root node, and in this root node we will have predictor 1 and value 1. So, predictor value combination based on which the split would be performed. So, some observation will fall in this part, other observation will fall in this part. Similarly, for next split we have to see that whether on this node or this node, where the reduction performing for these nodes, where the optimum split more reduction in impurity is going to take place. So, let us say the next impurity reduction, high impurity reduction happens in this particular node. So, let us say this is happens at variable P2 and V2, right. So, this is going to be our split 1, this is split 2. Then after this split is performed, some observation will go to this side, other observation will go to this part. Now, again for next split we will have to check between these three which on which particular node and which particular predictor value combination will improve the impurity further, right. Improve the impurity, the improvement reduction in impurity would be highest. So, let us say now that here at this node the reduction in impurity is highest, then this is, let us say the predictor value combination for the same is here. So, this is split 3, right. Now, so here again we will have some observation that will go into this part, some observation will go into this part, right. Now, for next split, now among these 4 nodes we will have to check which one is giving the most reduction in impurity. Let us say this is the split, this is the node, and we have P4 V4 and predictor value combination, and it will be split 4. So, the pruning sequence, so from this we wanted to derive the pruning sequence. So, we look at the pruning sequence, it is going to be this node, right. So, if it is node number 1, so if we follow the unique node numbers, that ordering that we discussed in the previous lecture, this is going to be node number 1, this is going to be 2, this is going to be 3, then 4, 5, 6, 7. So, our pruning sequence is first node number 1, then the second split happened at node number 3, then it happened at node number 2, then it happened at node number 6, right. So, first 4 splits in this example, if we look at first 4 splits, so they happen in this order. So, when we prune back the full grown tree to a certain level, we will have to follow this splitting pattern, right. So, let us say last if there are n number of splits, that means actually this is going to be n number of this is going to be equal to the decision nodes, number of decision nodes in full grown tree. So, therefore, we have to, when we start pruning the full grown tree back to the desired levels, we will start deleting the least important splits. That means splits which have done least amount of reduction in impurity. So, probably we will start from here and go our way back to the higher up to a level, so that we get to a point where the error on validation data is minimized. So essentially the exercise that we had performed in the previous lecture, the pruning that we had that we were following was based on this. So we just looked at the node numbers, and pruning was based on this. So we are following the sequence in the increasing order as per the node numbers. The optimal way of pruning that we want to follow is this one. So today we'll do an exercise in R wherein we'll follow this particular pruning sequence, and then we will understand few of the few more points using a particular exercise in R. So let's start. So first let's load this particular package XLSX. So let's go down. So all these things we have already done in previous lectures. Let's load this particular package as well. We would be requiring this R part, and one more package we would be requiring this one as well, R part dot plot. Now let's move to our data set. So promo offers.xlsx is the file, so we would like to import it here in our environment. So let's perform this. So it will take some time because it has this particular data set has 5,000 observations, so it will take slightly more time that we have been doing for other data sets, smaller data sets. So once this particular data set is loaded, we will go through some of the steps that we had performed in the previous lecture, and once that is done, so once the pruning specific steps start, then we will discuss what we have covered here. So you can see all the observation, 5,000 observations of 9 variables, all of them are loaded in our environment now. Let's remove any columns. Structure, these are the variables. So some of the steps we will have to quickly go through. For example, we did grouping of categories, so we will have to perform this again so that we are able to reach to the same point. So let's go through this code. We have already discussed this part before, so we are just going through this so that we are able to create the. So this is the now our data frame is ready. All the variables are in the appropriate types, data types, numerical and factors. Now let's do the partitioning. Already discussed these steps as well. Now let's build the full grown tree. So this is the code that we had used before. So you can see here, as we have discussed before, that xval value is 0, right? By default this is 10. So that is reserved for class validation. So because we want to build the full grown tree, so let's plot this. So this is our full grown tree. You can see quite messy as we had seen it in the previous lecture as well. So now let's move to the point where we want to discuss further. So the split variable and value combination, this particular table we have already discussed, we have gone through this, so we won't do this again. Performance of full grown tree, we have gone through that. So let's come back to the pruning process where, as I discussed, we followed a different pattern, different pattern for pruning. Now we will follow the actual pattern, the desired pattern based on complexity. So a pruning process, let's look at the number of total nodes in this particular tree. As you can see, number of total nodes 69, then 34 in the 34 decision nodes and 35 terminal nodes. So node numberings, you would see now certain steps that we had performed, you will see differences. Now toss1 is the argument that we want to compute at this point, which we would be passing on to the snip r part function. Now task 1, so as we have discussed that R part object, it has a frame attribute, and within that frame attribute it has the row numbers. So this we have discussed in previous lecture. So we will get the row numbers, we will convert it into integer vector, so that we will have the these numbers, unique node numbers, but the ordering is not as per the desired order. So now we'll create this data frame where we have these node numbers in the task 1, and we'll also have the variables, right? The variables involved at different nodes. So whether the decision nodes or leaf nodes. For leaf node, it would just mention leaf, as we have seen in tables in the previous lecture. Now for each node, we'll also have complexity value, which is also stored in the frame attribute, and within the frame we have this complexity variable, so it would be stored there. So let's create this data frame. You can see here, let's just scroll through this particular data frame. As you can see, first column is task 1, which is nothing but unique node numbering with respect to rows. The ordering of these we have already discussed in the previous class, the previous lecture, that it follows this sequence. Node numbering, we actually discussed it by showing the node numbers. So 1, then 2, and then 4, 8 in this fashion. These numberings are going to be there. Now once this data frame is there, now you would look, you can see that in the second column you can see the variables that are involved here, and the involved variable have the income is spending, then leave for each of these nodes, whether what predictor was used. If it was a decision node, what was the splitting variable for that decision node, and if it was leaf node, the leaf, it just mentioned it mentions as that that particular node is a leaf or terminal node. The corresponding complexity value, the complexity parameter concept that we talked about, that is used to control the size of the tree. So the corresponding complexity value for that particular node is also mentioned. So this is the value at which point the tree will collapse. So based on this, we can perform our pruning. So that will give us the that will control our tree size, and will give us the best prune tree and minimum error tree. So we'll do this. So before that, we'll like to order this particular data frame in decreasing order of complexity values, right? So the starting nodes from where the first split and then onwards other splits happen. So the starting nodes will have higher complexity values, right? Here the complexity value would be much higher. That is why this was the split number 1. Here the complexity value would be after this. So that is why it was split number 2, followed by split number 3 and split number 4. So we would like to order this particular data frame by complexity values, and once we order this particular data frame that we just saw by complexity values, we'll also get this sequence, right? Because this was the first split and the complexity value will be higher for this, right? So this would be first, then this was the second split, complexity value for this particular node is going to be the second one after this, so it will come here. So once we order this particular data frame, which is having complexity values for each node, we'll get this. So let's do this, execute this code. So you would see that before ordering, first we are trying to remove the leaf node. So we don't want to have a leaf node at this point. You would see there are many leaf nodes here. So we would like to remove the leaf node because the pruning is basically driven by the decision nodes, right? So once we remove the leaf nodes from this data frame, we'll get the new one. This is the one where. So this is the one, this is the new data frame that we can see DFP1. We have 34 observations, which is equal to the number of decision nodes that are there. These particular numbers we have already seen in the previous output. As you can see, 34 decision nodes and 35 terminal nodes. So once we remove the leaf nodes, the number of observations that are there in the new data frame, they are 34 equal to the number of, as you can see in the environment section, 34 equal to the number of decision nodes. Now once this is done, we can order, as we talked about. We want to obtain the nested sequence of splits based on complexity. So we'll order this data frame based on the complexity values, and once we order this, we'll get the desired nested sequence. Right. So let's execute this code. Now you would see that ordering has been done, and if we scroll back to see this table, now the first first entry is income variable. So this is the split number 1, and the complexity value is there. The second split is also having the same complexity values, right? We will discuss this further. What happens if the same complexity values are there? Then why income was the first split and education was the second split? Considering that, what happens when this is the scenario? So family size, then third split is based on this, having the third highest complexity value. So in this fashion, you can see that complexity values are decreasing. So this is how our tree is when we develop the full grown tree. So this is how this sequence determines how the splits are going to take place, and how the tree is going to be built. So once we start deciding about pruning, pruning this full grown tree, this is the process that we have to take, and therefore the earlier one that we did in previous lecture is not the desired process. Now you would see, because we have sorted this particular data frame, the row numbers have changed. You can see these are the original row numbers present in the original data frame DFP1. Now once sorting of that has been performed, the row numbers are still same. So we would like to change these row numbers to reflect the now DFP2. Let's look at the table again. You can see now the row numbers are also sorted. So 1 to 34 decision nodes, right? So once this is done, now we can start calculating our toss argument that we have to pass on to the snip.rpart function. So toss2 argument is simply nothing but the data frame that we have just created, the P2, the first variable toss1, that is going to be this argument. So let's create this toss2. Now what we are going to do is we are going to start our pruning process. And as we did in the last lecture, after every pruning we used to record the model, and we used to apply that model to score on training partition and other partition, validation and other validation partition, training and validation partition, so that later on we can compare the error rates, right? So the same thing will follow here, what we did in the last lecture, but now this time with the actual pruning sequence, the nested pruning sequence. So counter for nodes to be snipped off I, and once then we have this mod1 split v, the same variable that we used in the last lecture. This is going to store all the mod variables. Then mod1 train v, these variables are going to store the other things that we'll see, the scores, right? Mod1 train, so it will score, it will have the return value of predictor, so scored variable, right, list. Let's initialize them. Then we'll have these two vectors, error train v and error valid v. So these two vectors are the important for our plotting and to identify where the error on validation partition is minimizing. So let's initialize these two variables. Now you can see, as we discussed in the previous lecture, the loop is running for all the variables. So the in this particular case, you can see we are running this loop for all the decision nodes that are there, right? DFP2 in this particular column, now we have only the decision node. You can see again that in environment section DFP2 has just 34 observation that are the number of decision nodes in this particular tree. So we'll run this loop for the number of decision nodes. So some of the checks that we had done in the previous lecture, that code that we were eliminating the leaf, now we don't need to perform because we are dealing with only decision nodes. So the if section, you would see that we are comparing with the length of the toss2, that is the total number of nodes, and then because we would be pruning a node by node, so we are starting this particular process from I, that is 1, to the final node number, that is the last one. So first we start by pruning all nodes, then from node number 2 to the last one, node number 2 in the sequence, not node number 2 actually, node number 2 in sequence as is stored in toss2. So to show you the toss2 values, you can see toss2 1 to 34, so 136. So node number are actually unique node numbers are 136. So first we start by sniffing all the nodes, then we start by sniffing from this particular node to the remaining nodes, then we start from this particular node, that is 6, to the remaining nodes. So in this fashion we will start, and then a snip dot part function is being called for every time the loop is run, and we are recording we are correcting few more things. For example, CP table, once we create a new once we do the snipping, we will get the new model, new subtree model. So therefore we need to correct the CP table there. So the code for the same is there. Then once CP table is corrected, we will also have to correct the variable importance. The code for that is also there, right? So for this we are using an importance function, which is nothing but taken from the source code of prune.or part function. So there they have written this importance function, and we are directly using the same source code here in this our exercise, because this particular function is not available for us to call, is not part of the R part library. Once we load, we don't have access to this function. This is called internally within R part. So that is why we have to get that source code here, and to be able, and then we are using this particular here. So we will have to now create this function here. So that will do here. So you would see that in the environment section function, this importance function has been created. So we won't go into the detail of this particular function. This function is actually being called to once we create the subtree model, we would like to change the variable importance accordingly, right, in the subtree model. So the same thing is being done by calling this function. So then we keep on storing these all these subtree models. Then we score them off, score the training partition and the validation partition as we did in the last lecture, and then we are storing the error rates for training partition and validation partition, and this is the loop counter. So let's execute this code. So it is done. Now you would see that one thing I would like to point out here, that though we have been storing the models, but we cannot access all of them. You can see this is quite large list, and given 3 MB and just having 2 elements. So these R part object that we were trying to store in list, they are the size is quite big, so therefore it has not stored all the R part models, subtree models, and therefore only 2 are there. So but however we are interested in only the error rates. So let's create this data frame like we did in the previous lecture. So now let's look at these values for decision nodes in this ordering sequence, and you can see error training and error validation. So now when the for the first decision node, this is the training error and validation error. You can see that training error is slightly lower than the validation error when we start, and as we perform second split, then again the both are same. So there is not much decrease in error after second split. Then third, you would see that further the error has significantly decreased for the training as well as for the validation. So in this fashion, if you as we did in the last lecture, if you scroll down these error rates, the second column, that is error rate for the training part, it will keep on decreasing till it becomes 0, right, till it becomes 0 or close to 0, right. And and in the validation partition, you would see that error will keep on decreasing till one point, and after that it will start increasing. So you can see that this is the point where the error is minimum, right? So this is the point where the error is minimum, and then after this particular point it will hold up to for some more nodes, and then it will start increasing, right? It keeps on increasing. So with this now we can go to we can create this plot to visualize the same information, the information that we saw in table. So this is the plot that we had seen in previous lecture as well. Now with the correct pruning sequence, you can see that the plot which is this plot, this is this particular plot is for the validation data, the lower plot, the upper plot is for the validation data, and the lower plot is for the training partition. So for the training partition, you would see that the error keeps on decreasing till it becomes 0. For the validation part, you would see the error keeps on decreasing up to some point, and after that it will start start increasing, right? So probably here we need to, in this particular zone, we need to find out the point with minimum error tree like we did in the last lecture, and then within one standard deviation we will have to find out the best tree. So let's look at this value. Minimum error tree is this is the value which we already saw in the table. Then let's look at the particular number of decision nodes corresponding to this error value. There are 8 decision nodes. So minimum tree is can be obtained at 8 decision nodes. If we look at the graph again, so 8 decision node would be somewhere around here. So probably this particular straightening line you see. So all these nodes, they are nothing but representing the minimum error on validation partition. So whether they are 8, 9 or 10. So we can look at these values. If you are interested how many of these decision nodes are having the same number of same error, minimum error, 8, 9 and 10. So the subtree models with the decision nodes, 8 decision nodes and 9 decision nodes and 10 decision nodes, all 3 of them having the same amount of error on validation partition. But however, we'll just use the smallest tree here, and then we'll look at the standard error of error rate. So this is the value. Now we'll look at the range where we need to find the best pruned tree. So the best pruned tree should be having value less than this particular value error like we did in the last lecture, and should be greater than the error that we saw for the this one, minimum error tree, right? So this is the code for the same. So this part we have already discussed. So you can see best pruned tree is now coming at 5. So if you want to confirm this, we can go back to the label table, and we can see that number of decision node 8, this is the point where the minimum error tree is there. Now within that range we can see this particular tree is giving us the best pruned trees. This is within one standard deviation of minimum error tree. So this part we have already discussed. Now once this is done, once we have identified, then we can go ahead and create our best pruned tree model. So this is how again VPT we would like to contain these many number of decision nodes. So we can generate our TOS3 and then call the snip r part, and we'll have the best pruned tree. Now let's plot it. So this is our best pruned tree. Let's look at this particular plot. Now this particular best pruned tree, now the earlier one which we did in the previous lecture, because we are following the order of shorted order of node numbering, so we were getting the balanced tree. Now we get the right tree. You would see that this is not balanced. First income, then education, and then that sequence, that split sequence, the optimized split sequence is being followed in this particular example, right? So this is the best pruned tree that we can have. You can see 1, 2, 3, 4, 5 decision nodes are there, can see important variables, of course it is income, education, so income, education, family size and spending, so all of them figuring here. Now we can check the performance of this particular tree on different partitions. So you can see the performance 98.56, then on validation 97.9 close number, then on test 97.4, this is also close, so performance is quite good. So there could be another approach to follow this process that we discussed in the previous lecture as well, based on complexity value. So if we use the complexity value, for example, we have identified the best pruned tree. Now following the actual order, that is the split order. So in that we can find the appropriate complexity value, because we have this pruned function, this which we used in the previous lecture, which takes the CP value and prunes the tree based on that CP value. However, we will understand some of the problems with this particular function. For example, let's find out the complexity value for the best pruned tree that we have just identified, which was the tree with 5 decision nodes. So CP best is, this is the corresponding complexity value, and this you can see, TOS1 is 14, right, and so this will, using this particular value, so we can go back to the table and find out how many number of nodes are there here. So let's look at that table. So if we look at the value that we just saw there, 0.0515, so you can see this is the value 0.0515, and we can see that TOS1, so 1 2 3 4 5, so this is also 5. So the same corresponding tree is there, but however it might so happen that, so now we are discussing the problems that could be there with the prune function. Now the previous few values, sometimes if we run the same model, previous few values might also have the same complexity value. In that case, the tree with the smaller size would be selected by in this fashion. So if we do the pruning using the complexity values, even though we have identified, followed that process, minimum error tree and within one standard deviation best pruned tree, and now instead of the number of decision nodes, we use the complexity value to prune this tree. If the previous nodes they also had, they also had the same complexity value, so the pruning will happen at that level. So it might be, the tree size might reduce from 5 to 3 or 2 something in some scenarios, in some runs, and even in this data kit itself, if we do again the same thing, we do it again, then probably because of the sampling and the different observations that are going to be selected in the training partition, and therefore the different model that could be there because of the limitation on the sample size that we have, even though this is larger data set. So we can get different pruned tree using this particular prune function. So in this particular case, it comes out to be the same. So we can use prune function. We pass on the full grown tree model mod 1, and then the pruning value till the point where we would like to prune it. So we can see this. So this particular tree 1 2 3, you can see 4 nodes are there, and here we had 5 nodes. Now in this particular internal processing that happens in prune function, one more node, the spending one, it has been removed off. So that is the tree that we will have if we follow that complexity value, right. So the tree will collapse at that value, collapse at this value, right, and only 4 particular decision nodes would be there. Now further we can compare this particular case with the minimum error tree. So we can plot the minimum error tree as well. So this is going to be the corresponding complexity value. So this is following the prune function process. So you would see that so these are the nodes. You can see this is the value. So we look at we prune it. So this is the model that we get. So you can see minimum error tree model is much bigger even if we follow the prune function, right. You can see 1, 2, 3, 4, 5, 6, 7 nodes there, right? So we saw that size was 8. So in the pruned sequence, the last one is also removed off, so we get the 8 size. If you are interested in looking at other things, for example CP table and other things, so this particular aspect we have already discussed, right? So with this we stop here, and in the next lecture we will start our discussion on regression trees. Thank you.